please. Satellites. So imagine you've got a cannon. Perhaps you've imagined this before and you're like, ha ha ha, if I had a cannon, oh yeah. You'd be doing a lot of physics, right? No, that's not what you were thinking, right? Okay, you launch a cannonball, and let's just say for simplicity, you launch it horizontally. How far is it going to go? Or what would that depend upon? Gravity, the gravitational force pulling it down, right? Okay. So how big, or you could also just see it as the gravitational field. Okay, so little g. Anything else affecting it? How high up it is in the first place. If it's only a foot up off the ground, it's not going to go very far before it hits the ground. If it's 100 feet up in the air, then maybe a little farther, right? Also, how fast it's going, right? But in general, what's the cannonball going to do? It's going to hit the ground, right? Because what goes up must come down, yes? Not necessarily. What? That's outrageous. Okay, so we're assuming it has some particular range. That's projectile motion. If we launch it faster and from higher up, what are we going to do? It's going to go farther. It's going to be in the air for a longer time, but it will eventually hit the ground, right? Yeah, if we're talking about just launching a cannonball, sure. But if we can extrapolate this out to launching things really, really fast, then perhaps we can understand how satellites work. And this is what Newton did. Newton had never really heard of or even conceptualized things orbiting the Earth, other than, of course, the moon. But he said, you know what? If I could throw something really, really hard, I bet it would just start circling the Earth. Of course, that's really, really super duper hard. This picture showing it is, of course, not exactly to a good scale, but if we could get it going that fast, that would be something impressive. Yes? Okay. So, what do we mean by this? Let's see. Oops. Okay. So as we can see, they're going farther and farther, but because the Earth is flat, they just keep hitting the ground. Earth is flat, right? No. I remember hearing something recently. They discovered that the Earth was actually round, like, a few thousand years ago, right? Yes, okay. It wasn't Columbus that figured it out. We've known it's been round for a long time. So if we take the curvature of the Earth into account, with big explosions from our cannon, okay. Oh, no. Gonna make it. Oh, and then it, for some reason, freezes in space. Okay, let's zoom out some more, yes? Cannonball is making it all the way around. And then the people that launched the cannonball are kind of worried, because here comes the cannonball. Quick, open the back door, and it goes through. And it's coming back around. And oh boy, worried again, here it comes. Quick, someone grab hold of it as it goes by. Okay, grab it. Good. No. Okay, there we go. They were able to stop it. That's pretty impressive. Okay, so that's the basic idea, and we even call it Newton's cannon because Newton was the one that conceptualized this. This is the basic idea behind satellite motion. Okay, so you say, oh, well, that's cool. All I have to do is throw something really, really hard, and it'll orbit. Sure, but you have to clarify you throwing something and really, really hard, okay? A cannonball would need to be going 8 kilometers per second. 8 kilometers per second. Okay, you say, oh, it doesn't have to be a cannonball, it could be a tennis ball. Sure, okay. Doesn't matter, you're not throwing it that fast. Most of you probably don't even live 8 kilometers away from school, right? Imagine getting from here to home in 1 second. That'd be nice, yeah. Okay, that's how fast we'd be talking about. That's a huge, huge, huge speed. And that's also ignoring air resistance, okay? So you'd have to be up high enough to not have to worry about air drag. Of course, obviously up high enough to not have to worry about it hitting trees and mountains and buildings and other stuff, right? But certainly possible, right? Absolutely. We have man-made satellites in orbit right now. Yes? We've heard of these things?
Yeah.
Yes, okay. And the nice thing is, once they're in orbit, they're going to stay in orbit, assuming there's no other things that they might run into, whether it's other satellites or air resistance or whatever. There are various types of satellites, and they're there for various reasons. And there's the communication satellites and GPS satellites and the government satellites that we're not supposed to know about, and all these other things, right? Okay, and there's plenty of reasons that they're there, and there's plenty of space up in the sky, right? Well, sure, to some extent. But most satellites are traveling around pretty fast. In fact, most of the satellites are only taking about an hour and a half to go around the Earth. Who has seen the movie October Sky? Raise up. Okay. They used to show that in chemistry class a lot. Okay, it's cool stuff, but okay. So October Sky starts off, and they're showing Sputnik travel overhead. This was, many years ago. Of course, they're in a West Virginia mining town, and they say, "Oh, Sputnik, that doesn't have anything to do with us," and then story develops from there. But the point is, they're showing Sputnik overhead, and it's cruising along. So you say, oh, look, right up there. There it is. And then like a minute later, you'd say, oh, no, it's way over there now. Okay, and there it is. And then maybe a minute later, oh, it's just going over the horizon there. Okay, and then a minute later, it's gone. Okay, is it going to come back? Yeah, after a total of an hour and a half, and then it'll be right up where it started before, right? The point is, it takes 90 minutes for it to orbit. That would be the capital T, right? Okay? This is a special type of satellite. This is called geosynchronous. It's a few fancy words all smushed together. Anyone have any idea what those words are? Okay, geo, similar to geography. Geography is mapping out the Earth, right? Okay, in this case, geo is the Earth, right? Okay, so geo is referring to the Earth. And then we have synchronize, okay, which is, you can actually break that down into 2 smaller words, but synchronize, that means at the same time, right? Synchronize swimming, synchronize your watches, whatever. Okay, syn, S-Y-N, is like the same root as for synonym, right? Synonym means same, right? Same word, same meaning, whatever. Okay, yes. And chronos is referring to time. So, same time as the Earth, yes? Okay, that means instead of having a period of 90 minutes, it's going to have a period of 24 hours. So if you look up, and if you could actually see these satellites, you look up and you see the satellite, and you're like, oh, there it is, right up above. A minute later, still same spot. 10 minutes later, still the same spot. 2 hours later, still the same spot. 6 hours and 17 minutes, whatever it is, same spot above you. So they take 24 hours to orbit the Earth. That's the exact same amount of time as the Earth takes to rotate. Hence, synchronized with the Earth. Okay? So it depends on what the satellite is for. There's plenty of other types of satellites. And they go into very elliptical orbits and whatever else. In the movies, you'll often see like the spy satellites. You're like, oh, move this satellite so we can see something going on in this area. Okay, that would not be a geosynchronous satellite. Okay, that would be one of those, well, ones that we're not supposed to talk about. Okay. Okay. By the way, for anyone that thinks they can throw a ball at 8 kilometers per second, that'd be about 18,000 miles per hour. Right? Anyone ready for that? Stretch a little bit first. You got it? Okay. All right.